Hello everyone. Today we are going to talk about our work of proving Overshoot termination by omega regular decomposition. First, let me introduce our research problem. The termination problem of classical program asks whether all execution traces of a program are finite. But it becomes different in probabilistic setting. For example, there is a probabilistic program with probabilistic branching statement. Both of the branches have 0.5 probability to be executed. If an execution always goes through the bottom branch, the program will not terminate. But this case has only 0 probability. So, for probabilistic programs, we care about the overshoot termination. It asks whether a probabilistic program terminates with probability 1. The example program is overshooting terminating. We prove this by the martingale series. We try to find the so-called ranking Super-Martingales. Its value has a lower bound, and its expectation value is strictly decreasing. For example, the expression x is a ranking Super-Martingale for these programs, because we can easily find x has a lower bound 0, and the expectation value of x decreases by 1 after each loop iteration. So, the value of x becomes negative overshooting, and as a result, the program terminates overshooting. However, simple ranking Super-Martingales can hardly be applied to complex programs. Let's see these programs. There is no deterministic branching statement in the loop. Both of the values of x and y has a lower bound 0. However, in the top branch, ex decreases by 1, but ey does not change. And in the bottom branch, ey decreases by 1, but ex increases. So, it has no simple ranking Super-Martingale. To prove overshoot termination of these programs, the so-called lexicographic ranking Super-Martingale can be used. It is a lexicographic order over some expressions. For example, the expression y followed by x is a lexicographic ranking Super-Martingale. We have that either ey decreases or ex decreases, while ey does not increase after each loop iteration. As a result, the value of x or y becomes negative overshooting. However, the lexicographic order and the unaffecting condition are required in this method. Sometimes they are hard to be satisfied. So, we propose a new approach to proving overshoot termination. First, let's see a simple motivation example of our approach. This program has two basic traces. The trace row 1 goes through the top branch, and the row 2 goes through the bottom branch. Both of the branches change the value of x, so it has no lexicographic ranking Super-Martingale. We can find that the execution traces of the program is covered by arbitrary interleaving of row 1 and row 2. But the infinite repeat of row 1 can be proved to be almost surely terminating by a simple ranking Super-Martingale x. The infinite repeat of row 2 can also be proved to be almost surely terminating by a simple ranking Super-Martingale negative x. Moreover, the remaining trace set contains the traces of several row 1 followed by row 2, or several row 2 followed by row 1. All of them are infeasible, since the path conditions are unsatisfiable. So, it is trivially overshooting terminating. As a result, the whole program is overshooting terminating. The decomposition-based approach requires no lexicographic order or unaffecting conditions, so it is more powerful and has high generality. Here is the framework of our approach. It takes a probabilistic program P as input, and then builds a series of so-called certified stochastic modulars to cover the execution traces of the input probabilistic program. The certified stochastic modulars are built from the uncovered probabilistic traces. As a result, our approach can automatically decompose a probabilistic program into several omega-regular probabilistic trace sets, and then prove overshoot termination of each set by rather simple arguments. Before talking about the algorithm, we introduce some basic notions first. The first notion is the probabilistic control flow automata. It is a graphic representation of a probabilistic program. A PCFA can be viewed as a Booch automata. The location as a state of the Booch automata. The set of statements is the alphabet of the Booch automata. All locations except the termination location are the accepting states. So, the PCFA accepts all of its non-terminating traces. The second notion is the stochastic modular. A stochastic modular is also a PCFA. It is built from a Lexicographic probability complete trace. The probability complete means the trace should contain both of the branches of a probabilistic branching statement. A stochastic modular is also a Booch automata, but it has exactly one accepting state. So, a stochastic modular accepts all of the traces visiting the accepting state infinitely often. The third notion is the localized ranking Super-Martingales. The ranking Super-Martingale for probabilistic programs requires its expectation value to decrease strictly after every step. But the localized ranking Super-Martingales for stochastic modular just requires its expectation value to decrease strictly after the accepting state is visited. So, it can be viewed as a specialized variant of ranking Super-Martingale. We have the following lemma to prove almost sure termination of stochastic modulars. If a stochastic modular has a localized ranking Super-Martingale, the set of the trace accepted by it is almost surely terminating. The last one is the certified stochastic modular. A certified stochastic modular is a tuple containing a stochastic modular, a localized ranking Super-Martingale map, and an invariant map. Here is an example of a certified stochastic modular. The blue labels are the localized ranking Super-Martingale expressions on each location. Their expectation values decreased or do not change after each transition. The red labels are the invariants on each location. They ensure the value of the localized ranking Super-Martingale expressions are bounded. We have the following lemma that the set of the traces accepted by a certified stochastic modular is almost surely terminating. Now we present our algorithms. The algorithm takes a probabilistic program as input and decomposes it into several stochastic modulars. We use the previous probabilistic program as an input to show our algorithms. We first transform P into its probabilistic control flow automata. Then, we try to find a probabilistic trace in P but not in any certified stochastic modular Pi. If no such trace exists, all of the traces in P are covered by the union of Pi, and thus the almost sure termination of P is proved. Otherwise, we can find such a probabilistic trace ρ. Since ρ could be not probability complete, we complement ρ to a probability complete trace ρc on the probabilistic control flow automata. Next, we transform ρc into a stochastic modular. We usually choose the location of the loop hand as the accepting state of the stochastic modular. We also add a termination location to it. After that, we employ the template-based synthesis method to find a localized ranking Super-Martingale and an invariant map for it. So, we get a certified stochastic modular. Then, we try to extend it to a more general certified stochastic modular. The extended modular can accept more probabilistic traces instead of a single trace. This step is very important to the efficiency of our approach. Here, we just show the conservative extending rules. We first merge locations. If a statement connects two locations with the same labels, we merge these two locations and add the statement at a self-loop on the location. For example, the location L1 prime and L2 have the same labels, so we can merge L1 prime and L2. For the same reason, we can also merge L2 and 3 then. Next, we add transitions. If a statement does not affect the invariant and the decreasing property of the localized ranking Super-Martingale expressions between two locations, we add the statement between these two locations. For example, we can add any statement as a self-loop at location L0. We can also add more statements to other locations. Actually, we can use the more aggressive extending rule based on Floyd Hall logic. That makes our extending more effective. After the extending steps, we get the extended certified stochastic modular P1. We repeat the main loop until we find a suitable decomposition, or we cannot prove overshoot termination of some probabilistic trace. We have the following theorem to ensure the soundness of our decomposition-based approach. If a probabilistic program can be decomposed into several almost surely terminating stochastic modular, it is almost surely terminating. There is no complete method to prove almost sure termination, so we prove the relative completeness of our approach. If a probabilistic program has an n-dimensional lexicographic ranking Super-Martingale, it can also be decomposed into uncertified stochastic modulars. This theorem shows that our approach is at least as strong as the lexicographic ranking Super-Martingale-based approach. Moreover, there exist some examples can only solved by our approach, so our approach is strictly stronger than the lexicographic ranking Super-Martingale-based approach. We evaluate our approach by the available benchmarks from the work of lexicographic ranking Super-Martingale. The experimental results are presented in this table. The sharp D column is the number of the dimensions of the lexicographic ranking Super-Martingale. The sharp T column is the number of the trivial models used in our approach. All of the traces of a trivial model are infeasible. The sharp N column is the number of the certified stochastic modulars used in our approach. Moreover, the program ReL2 is not an almost surely terminating program. As we can see, our approach can solve all of the almost surely terminating benchmarks. The number of benchmarks solved by our approach is far more than that of the lexicographic ranking Super-Martingale-based approach. The results show the significant efficiency of our approach. In the end, let me summarize our work. We propose a decomposition-based approach to proving almost sure termination of probabilistic programs. The approach can automatically decompose a probabilistic program into several omega-regular probabilistic trace sets, and prove almost sure termination of each trace set by the rather simple argument. We also present the localized ranking Super-Martingale for proving almost sure termination of stochastic modulars. It can be synthesized more efficiently than the general ranking Super-Martingales. It can also help to extending the certified stochastic modulars more effectively. We prove the soundness and the relative completeness of our approach. Our approach is stronger than the lexicographic ranking Super-Martingale-based method in theory. The experimental results also shows the significant efficiency of our approach. Our approach can solve more benchmarks than the lexicographic ranking Super-Martingale based approach. That's all. Thanks.